So let's talk about initial conditions and boundary conditions for the heat equation. So if we've got the heat equation on a rod of length L, then we can think of the initial conditions as being a function, and we'll just call it u sub 0, on the interval from 0 to L. So x is between 0 and L. And as we've talked about before, Dirichlet boundary conditions correspond to fixing the value of u itself at the left boundary point 0, where maybe it's given by some function alpha of the variable time, and at the right boundary point L, where maybe it's given by some other function beta, as opposed to Noman boundary conditions, which refer to fixing the value of the x derivative of u at either end of the boundary at 0 or at L, where it's fixed equal to alpha or to beta respectively. You can also have Robin boundary conditions, and this is where you take a fixed linear combination like AU plus BU u sub x, and you evaluate it at 0 where it's set equal to alpha, and at L where it's set equal to beta. And so just to sort of sort out the relations between these and why some of them might be natural to think about, let's take a closer look. So suppose that we take some parameter h to be the heat transfer coefficient. So this represents how well thermal energy can pass from the bar to outside the bar, or in other words, how readily it can cross the interval at 0 or at L to leave the bar. So how well energy propagates across the boundary. That's what I should say. Okay. Okay, and so we talked about the diffusivity constant K before. So K talks about how well thermal energy can move around inside the object. H is how readily it moves from the inside of the object to outside. Okay, so then if we look at Newton's law of cooling, so Newton's law of cooling states that the rate of cooling of an object is proportional to the difference between the object's temperature and the ambient temperature. Okay, so what does that look like? Well, if we are at the if we are at 0, then this says that K times UX 0T is going to be proportional to, and then we have U, at this point minus alpha. So in this case here, we've got that this alpha is going to be the temperature on the interval from minus infinity to 0, right? So that's the ambient or external temperature at the left endpoint of the bar. And then we're also going to have KUX, now we're no longer at 0, we're at the other end of the bar, so we're at L. And this is going to be proportional to the temperature at, the difference between the temperature at L and the temperature outside. So in this case, the external temperature here, this is the temperature on the portion of from L off toward positive infinity. So that's the external part on the right ends of the bar. And so now we just need to think about the signs and whether these things are changing in the appropriate direction. And so looking here at L, at the right end point, what do we see? Well, the way this is written right now, it's saying that if the temperature in the bar is bigger than it is outside, so in other words, that this entire term on the right here is positive, if that one's positive, then we should actually have the temperature decreasing, right? Because if it's hotter in the bar than it is outside, the heat should be bleeding out through the boundary. So it should be decreasing, so we want a minus sign right here. Okay, and so by the same token, that means we would want to have a minus sign over here as well. But wait, in this case, we're actually looking at the derivative going in the opposite direction from the way that the heat is moving. The heat leaves the left endpoint in the negative direction. So that means that this actually needs to be a minus sign. And so most of the time, we don't write the minus signs because they both cancel. And so the way I had it originally was actually correct, although we didn't yet know it at the time. Okay, so yeah, so maybe I'll just go ahead and delete those guys. All right. So then you should think of this H as conductivity between the bar and the external environment, like how well it's connected, so how readily can the energy propagate sort of out through the boundary. And so conductivity is like the reciprocal of resistivity or insulation. So what that means then is that if we look as H tends to infinity, so in other words, as insulation tends to 0, then what do we expect to see? Well, if I rewrite the equation, we'll just look at the left endpoint at 0. So if I divide the H over to the other side, then we have K over H U sub x 0 T equals, I guess I don't need the parentheses anymore, U0 T minus alpha, right? And so as we take H to infinity, then what happens is the left side of this disappears, and we just end up with U0 T is equal to alpha. So this is perfect conduction, and from that we recover Dirichlet. So when there's no insulation between the endpoint of the bar and the external environment, then it should have exactly that temperature value there. On the other hand, if we take H to 0, so it becomes maximally insulated, so that there's no way that energy can get through the boundary, then looking at the equation, and I'll just rewrite it again with the H back on the other side. Then again, as we take the limit in H, this time H tending to 0, then what happens is this entire side will go to 0, and once that goes to 0, then we can divide the K off the other side, and we end up with homogeneous Noman conditions. So the homogeneous part just means equal to 0, and the Noman part means that we're talking about the x derivative of u. And so the moral of this story here is that the homogeneous Noman conditions, is what you want to use when you're talking about a situation that's totally insulated, so that nothing can enter or leave across the boundary.